Hi, my name is Mohit, and I'm going to talk to you about gRPC with Kotlin Coroutines. So my presentation is about, I'll share with you how to use gRPC, how to build a server and a client. So I'll show you a simple use case for using gRPC on the server side and how you could utilize channels and flows with it, and also look at how to consume it in an Android app. So how does gRPC work? So RPC stands for Remote Procedure Call, and Google has a framework that you could for it. So the way it works is that the way you would set it up is that you have a server in which you define a service in which you define all the RPC calls that you could make, that the client could make, and the service is defined using something called protocol buffers, which is a formatting language in which you could define all the different types of requests that could be made and the different types that the client could get and send. So you usually have clients in different languages like JavaScript, Python, or Java, or like a Kotlin, and your server is also like usually in a different language. So gRPC and Protobus, they provide a way for you to generate a stub on the client side that you could use to utilize to make RPC calls to the server. And there are different types of RPC calls that you could make that I'll show you what they are. And these RPC calls are made using HTTP2. So that's the general setup of a RPC setup. So for this example, I'm going to show you how to build a client and server using two different libraries. So on the server side, we're going to utilize Kroto-plus. On the client side, we're going to utilize a library called gRPC-Kotlin. So I'm using two different libraries to show you like two different technologies, but you may also have a server that was written many couple of years ago is using a different technology. So suppose you had a sample use case where you're trying to build an app that tracks your route as you go from point A to point B, and through your route you could check into different places. So you could, as you go and in your journey, you could click on a location on your map and get information about what's there. And you could also specify an area in your app and get all the locations in a particular area around the location. You could also, chat with others and, at a particular location, you could send messages to them. So how do we build such an app and implement such a use case on the server and client side? So the reason why I chose this use case is demonstrates all the different types of RPC calls that you could make. So let's look at how to build an RPC server. So we're going to do four things in order to do this. We're going to first see how we could configure our server using this library called Kroto-plus, and how do we define all those different types of RPC calls on the server side using protocol buffers. And we'll look at how to implement logic using channels and flows. So Kroto-plus is a library used a lot, and it provides you with Kotlin-friendly ways to deal with protocol buffers, and it provides you with coroutine bindings. So the way, if I was building this on the server side, I would create like a microservice, and I would break apart my code in different modules, where I have a server module that has code to read from the client, and I also have code I'll probably query a database when an RPC call is made. So I'll have a module for all my database logic, but also I'll have a module for my API where I define using Protobus all the RPC calls that could be made. And the common pattern is that this is defined in a folder called Proto, and then in the Proto folder you have a file. In this case, my example, I have a file called places.proto that I'll define all the RPC calls in. So what goes into that file? So let's look at the format and what you would put in there. So to define all the RPC calls that could be made. So first I'm defining a syntax. So I'm defining what version of protocol buffers that I'm going to use. So there's version 2 and 3. There are things in 3 which are not backwards compatible with 2. So I'm going to use version 3, and then I'm going to define my service like this. So service is a keyword, and then I have my name of my service, and what goes inside that block is all the RPC calls I can make. So the first type of call we'll look at is called a unary call. So the way a unary call works is that you have a client which is making a request to the server, and you're sending a location to the server. So in my example, I'm going to send a location to the server, and it's going to give me back what's at that location, a particular place. So this is the simplest RPC call. How do we define this? Here's an example of how to define it. So let's look at each part of this definition. First, you have your keyword RPC. So every RPC call begins with this keyword, and then you have your name of your RPC call that you're going to make get place, and then I'm specifying that the client is going to send a message which is a location, and I'm going to return. So returns is a keyword. I'm going to return a place. So how do I so this is the simplest RPC call, but how do I define these two requests and responses? So the way they're defined using protocol buffers is like this. I have a keyword called message. So every message is defined with this keyword. I have my name of my message, and I have the fields that are part of that message. And this location will have a latitude and a longitude. So each field that you declare has a particular type, and this type maps to a particular type in a language. So a double maps to, like in Java and double, you have int32 maps to an int64 will map to long in Java. So the protocol buffer compiler, when it generates your code, will map it to one of these language types. So each field that you declare in your protocol buffer file has a unique number. And this number is, you could choose from 1 through 15. It's used to encode the information in binary encoding. So the other thing is that so we have defined our location. How do we define our place type message? Similarly, the same thing. I have my message keyword. I have a string, but I'm also referencing an existing message called location in there in the second field. And then a place could be anything, a restaurant, a golf course, etc. So I could define an enum using protocol buffers where I have an enum here called place type, and then it specifies what type of place it is. So it could be a retail store, a restaurant, etc. So I have now defined my location and place message. And I could also define scalar values, like how many check-ins were at that location, how many comments reviews that people have put at that place. So this is the simplest RPC call that you could define like this. So there's also another type of RPC. So something else that you could do is that you could use built-in types. So here's an example. This is an RPC call that allows the client to check into a particular place. And the way you do that is that the client is going to send in what place that they're going to check into, but I want to return an empty, right, for this. How do I do that? So the protocol buffers library has built-in messages that I could utilize. For time, for example, they have this message for empty, and then the way I utilize that is by importing it from the library like this in my RPC service file, and then I could just update my RPC call like this, and it will return an empty type on the client side. So this is a simple how to use built-in like messages that are part of the protobuf library. So, but what makes RPC calls really great is the reason why I use them is because you could stream messages. So let's look at server-side streaming. So suppose I on the client side send a collection of cluster of locations, and I want to know all the different places at those locations. And the server could send a stream of data, not just one thing, but a stream of data where each item in this stream represents a particular place in that area. So how do you define that? So here's an example of it. This is a server-side streaming call where I have defined a new message in the area, which is going to represent not just one location, but a collection of locations. And this is how it looks like. So I'm referencing an existing message here. I'm providing two locations. And in that area, I want to find all the places. So what's different about this RPC call, what makes it streaming is I have added a stream keyword right there, right after returns. And that means that the server is going to return a stream of place messages. So that's what that stream keyword is for. So this is how you define a server streaming RPC call. What about a client streaming RPC call? In that previous example, the server was streaming something, but I could also stream something on my end. So I could give a collection of locations as I go in my track, and I could have the server return me some summary. So I have a server could return a summary in this use case. So this is this example of how you could do that. I have an RPC called record trip, and I'm sending a stream of locations that I could send it at different times, and the server will wait, and then it will collect all those locations, and I could have it return a just one single type, which is a summary. And keep in mind, it's not a streaming return type. So the way you do this is using the stream keyword again, but now I have it on the request side, not the response side. And I'm sending a single message on the response side from the server. So that's how a client streaming call looks. Well, what about a bidirectional call? And this is good for example, for polling, a really good use case. So, one common use case is building like a chat room where you have users that could comment, at different times. So all those comments that people could make could be sent as a stream to the server. And then the server gives you the replies the other people make as a stream also. So you have streaming on both sides, the client and the server. So this is the use case that I use RPC for. So now this is called bidirectional RPC call. So and keep in mind, I have on both the request and response side the stream keyword. Those are all the different types of calls that you could make. And this is how my service file is going to look using protocol buffers. So now I'm going to give this file to the protocol buff compiler. Is going to generate some code. And how does that work? So let's look at that. So when I perform a build, there's the protocol buff Gradle plugin. It's going to run that proto-C compiler, and the library, and what it's going to generate is some messages. Like for each message, like place, location, is going to generate a class for me to create it. It's also going into Kroto-plus library, will also generate coroutine bindings for those RPC calls that I just defined. So how does that look? So here's an example of what it would generate. So you have a message here, location, it maps to a Java class, which has a builder, and has a builder for setting each of those fields. So I could utilize this on like this using that builder, but what if I want to make it more Kotlin friendly, more DSL-like? So in the Kroto-plus library, there is a way to configure the compiler that it uses. There's a way to configure what generator that you want to use, some features of it. And I could have it generate inline functions like this by setting unwrap builders to true. And when I set that to true, what happens is that it generates an inline function like this. And keep in mind that parameter there is a lambda. Its receiver is a lambda.builder, and I could utilize this like this. So this looks more Kotlin idiomatic, much more DSL-like, and I could specify my location with latitude and longitude like this. So I could also have the library create DSL annotation markers like this. So that's how the library will create all the different types of ways to create my messages that I'm going to send. But what about creating my coroutine bindings? Let's look at that. So the way to configure it to create coroutines bindings for each of those RPC calls, you turn it on in your YAML file like this, specify like this. So when you do this, then you create a abstract class. The reason why it's an abstract class is because I will be able to implement, I will be able to inherit this and specify my own business logic that gets called when the RPC calls are made. So when you look at an RPC call like this is the simplest RPC call, Unary RPC call. Get a place and you get From a location, you get a place, and it gets translated into a suspending function like this, right? This. So, but what about, so how does that work? So client sends a request, and then on the server side, it creates and launches a coroutine when that Unary call is made. And it does it on a particular scope and on a particular dispatcher. And I could specify my own dispatcher, which I'll show you how that it could be used. So when that coroutine gets created, what the client sends the request gets call given to the suspending function, and then it churns, and then it computes something and runs the business logic and sends a response to the client. And when you look inside the library, you'll see here that over here, by calling new RPC scope is a method inside of that library that creates a scope on a context. As you can see, it launches a coroutine with an atomic start and handles the request. So what about a streaming call? And the way that gets mapped into coroutines is like this. What is interesting about this is that the first parameter is the actual type, but the second parameter, because it's streaming, gets mapped to a channel, a response channel that I could send things to. So a channel, if you don't know coroutines, so a channel is a way, a construct to send and receive messages. So when you look at a channel, it's defined as an interface in the coroutines library, and it inherits two different interfaces, send channel and receive channel, which have different concrete functionalities. Send channel allows me I could call this method to send something. I could check, is the channel closed for send, etc. And I would utilize this if I want to expose just that functionality for a channel. So I could send things to this response channel, different place, all different types of places. And what about a bidirectional call? How does that map? So the way a bidirectional call gets mapped is that now the first parameter, as you can see, is not a send channel, it's a receive channel. So I utilize that just to receive things from the client side and send it to the response channel. And you can see it's a receive channel type. So receive channel just has a functionality to receive something. I could check is the channel closed for receive, etc. And I could just expose that functionality with this interface of a channel. So that's how they built that API for these RPC calls, this Kroto-plus library. So what happens underneath the hood? Underneath the hood, what happens in the library is launches a coroutine, and it defines a channel, and I send my request to it, and it gets it, and then I could run my business logic, and then I could send something to the receive channel, and it sends it to the client. So that's how it works underneath the hood. And then, so it generates the low-level code to make the RPC calls for each of these methods in this abstract class. So I could override it and give my own business logic that I want to execute. So I'm going to create this class called place service. I'm going to inherit that class. And then what I'm going to do is that I could define my own context that I want to, my own dispatcher that I want to run. By default, it uses dispatchers.default. But I could specify like IO. But for testability, I want to be able to, in my test, inject a test coroutine dispatcher so that I could inject it in this class, and like this, and I could utilize that injected dispatcher like this. So I'm overriding this field called initial context to do this. So how do I write the business logic for a function like get place? So to do this, I would probably query my database to get all the places and filter it out. To filter it out to find the one that the client requests for a particular location like this, and I could send it back, and I could create a place object like this using my message builders, my Kotlin friendly DSL, and I could return it like this. So this is a simple example of implementing a Unary RPC call. So what about how do you implement a server-side streaming call? So the way you might do that is that also here, query your database to get all the places for an area. So you would have business logic for that. And you could, in a for each, this is one way to do it, where each of the places that you find, you could send it to the channel like this, to the response channel. One question that comes up is that, how do I close the channel? So when you look underneath the hood, like in the library, you'll see that it does it for you. It will close the response channel once your coroutine goes to the end of the line. After it executes your business logic. So what about an exception occurs? Excuse me. What about an exception that occurs? So if an exception occurs, and when you look underneath the hood in the library, you'll see that it wraps whatever your business logic is in a try and catch and finally, and it will do cleanup and cancel the scope and propagate the error to the client. And so that's how error handling is done with that. So in the end, you with the service, you could implement all these different types of methods that you want to execute when these RPC calls are made. So now we have implemented, a server, and how do we configure our server and start it and specify what host and port to start it on. So Kroto-plus library is built on top of gRPC Java. And if you don't want to use coroutines, then you could just use gRPC Java. So gRPC Java has a way to create, to specify a server builder to specify what port and what services that you want to hook into. So you could utilize this by creating your server like this for a particular port. You could add any number of services that you want, not just one, like in this example. And then after you build your server, you could specify that you're going to start it, and then you can hook into your runtime like this to shut it down. So then you would start it like this. You have a main method like in your microservice, and you could configure your server on a port, and then start it, and it will block until shutdown. Like it will keep running until you manually shut it down, listening to your requests. So that's how you configure your server, and now we have a server set up that we could consume on the client side. So there are a couple of resources that you could check out. You could check out the Kroto-plus library and protocol buffers to see, what are different scalar types. You could also check out. So some people use Spring which also has support for gRPC. There is a framework that I use called Micronaut, which also has a built-in support for gRPC, and I highly recommend that framework. It's awesome. So you could check out those libraries. So let's look at lastly, how to consume what we just built in an Android app, building a gRPC client. So the library that we'll utilize, which was released a couple of months ago, is called gRPC-Kotlin. This is also built on gRPC Java. So the library that I use, so how does it work? So I define, as you saw, all the RPC calls on the server side. I'm going to copy that over and bring that on the client side in my Android app. I'm going to create a Proto folder. I'm going to set up my Proto buffer Gradle plugin to read from it, generate code, and it will generate a client stub that I could use, which has a lower level logic that knows how to make a request to the server. So what is inside of that stub? Let's look at that. How does it map each of the RPC calls? So this call, just like on the server side, will be a suspending method, like get place, give a location, get a place. So how does a streaming call get mapped? So if we hear the streaming call, the way it gets mapped is that the stream place gets mapped to a flow. The server will be returning me a flow of places. And what about a bidirectional streaming call? A bidirectional streaming call, both the request and the response, they get mapped as flows. So I'm going to give a flow of comments in this example to the server. I'm going to get a flow of replies. So it will auto-generate code for each of these methods. And how do we utilize this? Generate a coroutine stub. So first thing you need to do is build a channel. But keep in mind, this is not a channel like in coroutines. This is a channel concept in gRPC. And they provide you with they also provide like an OKHTTP channel builder or Netty channel builder. So here I'm going to use a managed channel builder, generic one, which I'm going to specify what address host my server that I'm going to hit, and what port is it on. If I'm using HTTPS, I'll use transport security, and I'll have built my managed channel object. I could also specify an interceptor that will get called every time when I make an RPC call. This is good for like logging, etc. So when I do this, I have my managed channel object that I need to create. Then I'm going to inject it into this generated stub that the library generates, gRPC-Kotlin. And then I could use this to make actual requests. And the way you might implement that, in this example, I'm using view models from architecture components. I have injected my client in there, and then that I could utilize it like this. In this example, I'm launching a coroutine on a view model scope, and I'm launching coroutine, and I'm calling client.get place on it to get the for a location, get a place. The simplest RPC call that you could make. Over here in this example, which is a streaming, this is a server streaming call where it returns me a flow. So what happens if an exception gets thrown? Well, this is going to crash, but you can handle exceptions by doing places.catch, and you could return like an either type from arrow if you want. So that's one way to handle it. Another way you could handle exceptions in coroutines by injecting into the context of this coroutine an exception handler. But I recommend like flow.catch extension to use. So the other thing, how does a bidirectional call get get mapped? So if you have a bidirectional call, like this library takes in a flow. So you could have like a hot stream. So you could model that using a channel in your application if you're building like a chat room app, where anyone when you're sending comments, you could push to this channel all the comments that you're sending on the client side. But then I could convert it, I could bridge that channel to a flow using consume as flow. If you're using a broadcast channel, you could do there is a method called as flow. It's not consume as flow, it's called as flow, and that method will open a subscription underneath the hood on that broadcast channel. So that's a pattern that you could utilize. So I'm sending that to a flow, to this generated chat method, and then I could collect whatever the server will give me back. So the way this works is that I could send one thing, and then the server could decide to send me a message, or it could wait until I send multiple things. So it depends on the business logic that you implement. So in my view model, I'll have basically like methods for all of these implemented and business logic for them. So that's how I could utilize this client. But the question is, what happens underneath the hood when I call these coroutine methods on the client, suspending methods? What happens inside of that? So inside, what it does is what the library gRPC-Kotlin does is that it has a custom flow that it creates, and inside of that flow, it's going to take whatever you give to it. It's going to create a coroutine. We call it a consumer coroutine. And inside of it, since this library is built on top of gRPC Java, it will tell it, hey, start the client. Start the client. And after you start it, it gives it a request. And then it goes out, and then you get a response back. The response that you get back gets put into an array buffer channel size 1. And when it adds a response to this channel. It could be one response or two response. It will add all of them. And it will also, since all of this logic that I just showed, these two boxes are inside of a flow, it will call emit on that response to give it to the client side. So to you on the client side, what you're exposed on your end is a flow of responses. And so this is the setup, overall setup of the library, and how it uses coroutines to make any type of request in any type of RPC call. So that's how you interact using your view model with the client stub and how it works under the hood. There are libraries and resources that you could look at, like gRPC-Kotlin library. There's also a library called Wire. Wire is a really great library, a bit different in the way it sets it up. It has the concept of a gRPC client that you could use. So but it doesn't support everything in Proto 3, which is why I wasn't able to use it. But it's a really great library by Square, and so in this presentation we looked at how to build a server using gRPC server using Kroto-plus, and also how to consume it on the Android side using gRPC-Kotlin. We looked at two different libraries and how they utilize coroutines. So I have a website, codingwithmohit.com, that you could check out. And I have written posts on like how do you test coroutines and how channels and flows work, and all that information is useful as you're interacting, as you're writing tests for your view model that I just showed. And you could check out my blog posts. I wrote a blog post on unit testing, delays, errors, and retries. So all those things are applicable here. I also wrote a blog post called Kotlin Assert Flow Delight long ago, which is now Turbine by Square. On that's the pattern that I use on asserting with flows. So if you, on the client side, you make an RPC call like to list places, returns a flow. In my tests, like I could utilize this library and write more fluent like testing assertions for my view model. So also wrote on how channels and flows were, given more presentations on that. You could check that out if you want to learn about more use cases on using channels and flows. So that's my presentation. I hope that was helpful and you learned a little bit about gRPC. What's really useful that I utilize is bidirectional streaming, which is very useful for me personally. Thank you to Kotlin London for allowing me to present from New York, and thank you to Enzo and all the organizers for this opportunity.
Thanks to you. Really nice talk. Thanks very much.